for today's talk, I'm going to be focusing on kind of going deep into active preference learning and specifically looking at how we can use that for reward functions within reinforcement learning. And so the goal here is to efficiently be able to learn reward functions while encoding a human's preference for how any sort of dynamical system should work. So if you think about a machine or any sort of robot, and so specifically, I'm going to be looking at how an active preference-based Gaussian process regression technique can be used to learn reward functions. So before we get into that, I just wanted to do a quick recap of RL. I'm sure a lot of us in the audience are already familiar with this, but obviously the key mathematical framework behind this is the Markov decision process. And so within this, you have a set of states which are represented by S. You have a set of possible actions that can be taken, which is represented as the letter A as a function of S that represents any sort of action that you can take within each state. You have a real reward function, which is represented by R as a function of S. And then you have a transition model that is looking at the transition that happens from one state to another state. And so really the goal is for the agent to work on taking different actions and then try to maximize the rewards in this environment. And so let's say you have a task where you have a user that wants a robot to learn from a task. The user itself knows the internal reward function that they want the robot to learn, but the robot itself doesn't actually know what this reward function is. And so today it's very difficult to teleoperate as a human with these robots in doing a lot of different tasks, because a lot of these tasks that are often very complex for robots have a very high degree of freedom. And so the success of reinforcement learning, though, depends very, very heavily on how you can put that prior knowledge into the definition of a reward function. But coming up with a reward function is a very complex task. And so although often a reward function can also be transferable and can kind of be described as like a compact definition of the learning task, the actual learning policy is very sensitive to small changes. So because of this sensitivity in changes, it often leads to very different behaviors depending on the relative values of those actual rewards. So this is why the choice of the reward function is a very crucial thing in the impact of the success for the learner and the many tasks that it does, especially within robotics, where often there's a very high amount of reward engineering that happens. So if I had to kind of categorize, I would say these are the four main categories that you see on the screen that are responsible for the difficulties within reward engineering. So the first one is reward hacking. And this is when the agent will try to maximize the given reward that you've defined without actually performing the intended task. And this kind of happens very often, and this is the most common area of development. The second thing you have that could happen is reward shaping. And so in many applications, the reward does not only actually define the goal that you're trying to achieve, but also guides the agent on how to actually get the correct solution. So that itself is known as reward shaping. But being able to strike a balance between the goal definition and the guidance task is often very difficult to do for the experimenter. The third area is infinite rewards. And so some applications require infinite rewards because certain events should just be avoided at any cost at all. And then the fourth area is multi-objective trade-offs. And so this is required to when it's required to actually aggregate multiple numeric reward signals. There's also a trade-off that is required, but the trade-off is often not explicitly known. And so this is why different parameterizations have to be evaluated for actually obtaining a policy that correlates with the expected outcome that you're hoping to achieve. So looking at a specific task, this example that I have on the screen, you have a user that wants the robot to learn and play a variant of mini golf. But the targets that you see on the ground here, contain different squares and different shapes. And so the user knows these squares, but the robot itself, again, doesn't know that those squares are there or what those squares actually look like. So this is where preference-based learning can be very useful, because the robot itself can actually show the user the different trajectories to which the user can then select and pick which trajectories they prefer to actually accomplish the given task. Now, a lot of prior work in this space assumed that the reward functions are linear in some sort of trajectory features. And obviously these trajectory features are very specific to the test and the scenario that you are in. So for example, in the mini golf example, the task, let's say the distance of the balls from the actual target could be the features, but you can't just use and just learn the weights from these features, because these features are also very incredibly difficult to design. So there's an importance. These are also, the features themselves are really important, because if they're not well designed, then the system can totally fail. And so in this mini golf example, you could say it could be sufficient to just have the shot speed and, let's say, the shot angle as our trajectory features that will successfully hit the ball into one of the targets. But with linear rewards, the optimal shot is actually going to end up in either one of these four blue quadrants, because the robot will try to either maximize or minimize the speed and the angle. Now, what we could do is, we could keep the linear function if we defined an if feature for each and every target to represent the equal distance between the wall and the target, but obviously this approach would not be very scalable. And so instead, what we want is actually to model the reward as a nonlinear function of features. So this allows for the optimal behavior to correspond with any point within this highlighted region. And so if you can learn such a nonlinear function, then the feature design also becomes very easy, because the reward function itself can actually handle a lot of that itself. So there's kind of two main reasons why I think preference-based learning and active-based learning are really important. And the first kind of problem is it's just very difficult for people to provide demonstrations of the desired system trajectory, especially in a scenario where there's such a high degree of freedom robot arm that's in motion. Or it's also very difficult to even assign how much numerical reward an action or trajectory should actually be getting. And this is where preference-based learning can be really, really valuable, because you can use it to get the person to actually define and provide input to the system based on a relative preference between the trajectories that the robot is showing and kind of demonstrating. The other issue is that the learned reward function strongly depends on what type of environments and trajectories were actually experienced during the training phase. So this problem can be solved through active learning, where the system can decide on what preference queries to actually make. And there's also, a lot of research that's found that active learning and the algorithm actually converges a lot faster to the desired reward because of using active learning. So before I get into how we can actually, use different algorithms to model this reward function, I think it's important to understand the main differences between passive RL and just active RL, and then also just why active RL makes more sense to solve this problem. And I think genuinely, active RL makes more sense for a lot of problems as well. And so let's take a look at this example. And what you can see here on the screen is just, you see a bunch of numerical values. Those are essentially just the reward values for all of the states on the represented in this scenario. And so as an agent is exploring this environment, the agent doesn't actually have access to any of the rewards that we're seeing on the screen. But what it does have access to are the direct interactions that it's doing with the environment. So it's trying different actions which lead it to take different paths. And that's shown through the red arrows and how they're kind of all over the place in a lot of different directions. And so the idea is that we're considering an algorithm that's input is going to be a history of what the agent tried to do. So the actions that it took. And then the resulting transitions that occurred and the rewards that actually came from those actions and transitions. And so if we were able to learn a good policy or utility function from this information, or just really anything about the environment, then what we've done is passive RL. And so the key kind of areas within passive RL, the first one is direct utility estimation. And so the algorithm gets recordings of an agent that's running a fixed policy. So essentially, we're watching this agent try to get rewards in some environment by running on a fixed policy. And so we can then go in, use the rewards, the state transitions, the actions that we know the policy was trying to execute on, and then from all of this information, try to estimate and attempt to find a utility function. And so an agent's utility function, it's defined differently in different ways, but it can be just defined as in terms of the agent's history of interactions with its environments. And so essentially we treat each time step, each action that's taken in the recordings as an example of what the future could be. So using past information and data to then make a prediction on what the future rewards will be, to then directly estimate the utility using those samples. The second area is within adaptive dynamic programming. And so this is essentially just estimating the transition probabilities. So this is a probability that the agent will move from one state to another state. And then running a policy iteration on top of that using our estimated rewards and our estimated transition probabilities. Third area is temporal difference learning. And this is just a strategy that updates our current estimates of the utilities every single time that we make a transition where we take an action or end up in a new or even just the same state, but just any sort of transition that's happening. So we can then compare the utility of the state that we are currently in versus the state that we actually transition to. And so we treat that as a sample of what we think our expected or current expected future utility or reward is going to be. And then we compare that to our current estimate. And so based on kind of what you think the future utility will be versus the current estimate, if that ends up being bigger than it should be, then we just increase our estimate. But if it ends up being smaller than it should be, then we just decrease our estimate. Now, the main problem with passive RL is that there isn't really a good way to update the policy. So even after we estimate the utilities, there's not really a good way to update the policy because we don't know what the direct transition probabilities are, or at least that's the case with the direct utility estimation. But also with ADP, we are estimating the transition probabilities, but we don't actually have a very good estimate because we're just sampling from all the transitions that happen when we take actions according to the fixed policy. And so this means that we have a very limited sample of what the transitions will be for any action that's not actually in that original fixed policy. And so what we're essentially doing is we're estimating the U's that you see in this equation, and we have a good idea for the U's, which is just the utilities, because we can use kind of these passive recordings of the agent running around in the environment to predict that. But we can only get a good estimate of the transition probabilities from the actions in our policy, because because the policy itself is fixed. And so we can't really estimate the transition probabilities for any action that isn't within that policy. And this is where ActiveRL comes in, because within ActiveRL, we now have the ability to choose the actions for the agents to try, and that gives us the opportunity to actually try actions that aren't within our policy. And ActiveRL itself is all about kind of the question that we commonly hear regarding exploration versus exploitation. So exploitation is really just using the best policy that we have right now, versus exploration, which is just the opposite. So not using the best policy we have right now. And often the common approach that's kind of taken, and I'd say kind of a high level scenario, is just to choose actions randomly. And although that works fine in some scenarios, it can be really bad for other scenarios. And so to be more efficient, you can also shrink the probability of that random action over time. That is, most of the time you're going to take the optimal policy, so you have good rewards. But within any state that is unknown or hasn't been experienced before, you will likely also be taking random actions to try and figure that out. But really the goal is, if you've already visited that state and you've already been to that state, then you'd want to just take that random action not as often. And so that kind of helps to shrink, I guess, the probability and make this process a little bit more efficient. And so one way to do this is to always try using our current estimates of transition probabilities and utilities, and to pick the action that will actually give us the highest future reward. And so you won't be estimating the actual true utility, but it will rather be a kind of over-optimistic version. And so that's what the U plus really represents. That is the overestimated utility. And then the N represents the number of times we've actually tried out the transition A from state S. And so the F is going to be, any function that tells you how much you should trust the current estimates of your utility. And if you don't actually trust the current estimate of the utility, then you can kind of go towards overestimating it. And so assuming that there will be a great reward if you try to take that action. Now, there's different ways in which you can kind of model this reward function, but one of the ways that is commonly explored is through GP, because they can be more efficiently used with a small number of data sets. There is a lot of work just using like simple neural networks, but neural networks are not really efficient because you need a lot of data and a lot of training time to actually get that model to efficiently learn the reward function. So that's kind of one of the benefits of GP and why it's commonly used. And so the idea that I'm speaking about here was actually presented in the research paper that I have linked at the bottom of this slide. So if you're interested, definitely check that out to get kind of a deeper insight, because I'm just going to be going over it at a high level. But essentially what we want to do is improve our data efficiency as much as possible, because currently every query only gives you about, at most, just like one bit of information. But this is why, on top of using the GP, you have to actively generate the queries to maximize the information gain or the data efficiency. And so the robot will take on a GP. And so using this model, it will generate the pair of trajectories that will give the highest expected information gain. The robot will then show those trajectories to the user, who will then respond to the query and kind of pick the best trajectory that it thinks will lead to the optimal result or the goal that it would like to achieve, which in this case is throwing the ball into one of those squares on the floor. And so this response is then stored into a database based on what the user says. And then in this specific scenario, they used a probit model to actually record and use the human responses. So depending on how close the rewards are to each other, this also produces probabilities that are either close or different. But using this model, the data set will also give you a likelihood function, which can then be used for fitting the GP. And so if it doesn't fall into any of the class of GPs, then you can also approximate this GP, which they kind of explain more in depth in the paper if you're interested. But then essentially this entire process is then repeated. And so obviously I just touched the tip of really exciting research that is going on in this space. I just wanted to link two papers that I think are great if you guys are interested, alongside the paper that I had on the previous slide. So these papers explain batch active preference learning for reward functions, as well as just kind of active preference-based learning for reward functions. And specifically, they looked at self-driving cars in these scenarios, but a lot of this can also be applied to robots with high degrees of freedom tasks that they have to accomplish. So highly recommend checking out these papers to just get a deeper understanding, and if you are interested, to learn more. And yeah, this is my social media. If any of you guys want to get in touch, I'm active on Twitter, LinkedIn. You can also email me, as well as just check out my personal website if you want to just see some of the projects that I've been working on or want to get in touch about anything.
If we want to reduce the number of iterations or steps, which type of reward or learning can be used?
Yeah. So, I mean, I think there's a lot of different types of rewards and learning processes that can be used. I think the common one that I looked at in this scenario was obviously using GPs, and they got some really good results in terms of getting like quick conversions on the actual model, and also I think they were able to reduce the steps by a lot through the paper and the process that they use. So I highly recommend checking out their paper. Again, it talks a lot more about how they actually did that and the process in which they did that. And then there's also a paper for batch active preference-based learning. And so I think that is also a great way. I think with reward function learning, it's kind of really complex because a lot of it is very trial and error. And so it ends up taking a lot of time, and that's kind of the common approach. And so I think the goal with active preference-based learning is being able to reduce that probability a little bit and also having kind of full control over the policy. And so that's one of the benefits. Again, I'm not too sure about how well they've been able to actually reduce the steps. But I would check out some of the papers that I linked to kind of get a deeper insight into that.
Scalability of GPs. With GPs, what is the limit on the number of data samples?
Yeah, so I don't think they had a limit for their kind of the work they did, but it was definitely like a few data samples. It wasn't as much as, again, with neural networks, but one of the reasons why they used GP over neural networks was also just for being able to train it on less data, because like, again, you have a lot more data samples that you need to use within neural networks. And so I think I'm not sure about the specific limit that they had, but they did have obviously less data that they used than a lot of the neural network approaches that they spoke about. And so, yeah, I don't know a specific amount, but I think that was one of the reasons they actually went with the GP approach, was just so they could use less data and also have less kind of computation and training that they had to do for the model.
Outstanding.
But yeah, I think the scalability question is a really good question too, because it's hard to scale this across a lot of other examples. Like this works really well in this specific scenario and also for this task, but actually scaling it further across other tasks and just a few examples is a huge problem with this approach. Yeah.